to do, as we said, perfect. So go to your RoboFlow, sign in, export the data, as we said, into the darknet format. And then when you come here, you should have the following files set up. Let's close this. Yes, so this one is pretty easy. We have already looked at it. And as we said yesterday, you're going to have to make the following change. Each YOLO layer in your config, whatever config you're going to choose, you must change the number of classes manually, of course, and you must change the number of filters before every single YOLO layer to a very strict formula, which is 5 plus the number of classes times 3. 5 plus the number of classes times 3. So the number of classes, pretty easy, self-explanatory. The 5 or the 5 plus the number of classes just refers to the X, Y, and the width and height coordinates, plus whether this location contains an object. So we have 5 pixel values, or 5, how can we say, 5 channels, or you could think of them as just 5 output values, which are the X, Y, width and height, plus the objectiveness or the objectness score. As we said, plus the number of classes multiplied by 3, which refers to the 3 types of anchors, which are horizontal, vertical, and square. So this is for the number of filters. As we said, you're going to have to do this as many times as you have YOLO layers. Of course, for example, this convolutional layer that is before this one, you don't change the number of filters. So the number of filters must remain the same. You don't change that. You only change it here manually for the final convolutional layer just before a YOLO layer. And you do that for every single YOLO layer. In this file, we have 2 YOLO layers, but for something a little bit bigger, we could have something like, let's go with X, for example. Let's see how many YOLO layers do we have. Again, 3, just as the typical YOLO for the same thing. So this one is for the first file, as we said. The config file is pretty easy for the configuration of the weights or for the configuration of the types of layers that we will be using. Now that it is done, you're going to have to first start working on the next level, which is the following. So object.names is just a simple file which contains the list of object names, right? So for example, if you're detecting 5 objects, you must have 5 words in this order. Each class should come, in its own line. And the end of this, the extension of this file is just .names, but it's a simple txt file, right? It's just an extension. The other type or the other file, which is a very simple file, is called the object.data file. And this file is pretty simple. You just refer to where do you put your training data, where do you put your testing data, and where do you put your names of the classes. Keep in mind that there are 2 ways to refer to this train and valid, either using a txt file, and inside the txt file, every line refers to a location of an image, or you just put the name of a certain directory. So for example, you are putting all the train data set into a train folder. So you put the name of the train folder in here. 2 options, either the train folder or the txt file with the actual location of each individual image. After that, that's all you'll have to do. It's pretty simple, pretty easy, pretty straightforward. You start immediately doing the training. The majority of these guidelines are, as you can see, a little bit tough because there is a lot of them, and mainly because he expects you will be annotating them using a open source, what is it called? Labeling, what is it called? Software. I forgot which one it is, but it's a very not that good software that does it locally. So you cannot collaborate with your friends and stuff like that. But RoboFlow already does all of these configs for you. So it's nice to know them, but if you're going to be using your RoboFlow, it will immediately do them. Even if you're not going to be using RoboFlow and for some reason you went with something a little bit more, local, so it's not a website, but more of a software, then there are hundreds of Python repositories that can help you convert from whatever data format your data set is in to the YOLO v4 data format, specifically for the darknet. Here you will just run the training. Pretty simple. It gives you exactly the same numbers as you would expect. So the loss functions, how are they progressing? I think every 100 or every 1,000 iteration, it runs a validation set. So it just evaluates whether the model is good or not, and it saves or stores the best model. And as you can see, it does give very good results very quickly. As we said yesterday, for mean average precision, if it's above 60%, it's already very good. It usually depends on the number of channels, as we said, but if it is above 60%, that's honestly a great start already. So that's mainly it for the YOLO V4, as you have now the links for all of them. For the labs, I would expect you, or even if you have like your project about object detection, you should experiment with both YOLO V4 and YOLO V8. So I will be releasing the homework hopefully today. The homework is going to be pretty easy. As we said, you just take 100 pictures, annotate those 100 pictures, and then train YOLO V4, YOLO V8. Build a simple report. Here's YOLO V4. Here are the results. Here is the time inference and the time of training. Here are the time of inference and time of training for YOLO V8. Here is the results for each individual one. And that's it. So it's a very simple report. Everything will be expected from you to be in a very, your own, of course, words, your own format. So I will not be providing you with any templates, no code, no nothing. You will be doing the job from scratch as if you are doing it in a company. Now, that said, let's get started with the actual segmentation, what it calls, or course lecture. Right. Segmentation. Mm-hmm. So for the segmentation lecture, it's going to be a pretty easy one. It's going to be very simple, as you've already seen the object detection lecture. It's going to be kind of a, let's call it a continuation of that, but you will also be seeing new architectures, hopefully different architectures and different techniques. But before we go into that, I would just like to confirm again with Professor Khan, what did you see? So did you speak already with Professor Khan about the concept of autoencoders and variational autoencoders? Yet. So this lecture is going to be a little bit hard. So yeah, I will try to go as many details about both autoencoders and variational autoencoders, but I will not go into the mathematical loss functions. When it comes to the mathematical loss functions, pretty easy with Professor Khan, I think, or Professor Fahim in the either advanced machine learning course or the advanced computer vision course. But in both of these courses, you will be studying variational autoencoders and their loss functions. Their loss functions are actually extremely useful, especially if you want to go and study about things like, what are they called? Those new diffusion models, or even basic generative models. The loss functions for the VAEs are actually quite a good introduction to that field. So definitely something that you should at least look into. If you're not going to have it in the future courses, try at least to look at it. It's a very simple one. One simple YouTube video should help you with that. All right, then. So let's get started. The start of this lecture is going to be about autoencoders in general. And then we will go specifically into variational autoencoders and speak about why and how can we use them to extract features, and how can we use them to even generate new images. And then we will speak about segmentation and, of course, the different types of segmentations, or the two major big parts of segmentation. Of course, now there are even more types of segmentations, but we will be speaking about the two most famous ones. And then we will go with the architectures for one of them, which is semantic segmentation. We will speak about UNet, we will speak about SegNet, and of course about autoencoders. That's why we studied them in the first place. And then we will go to the final RCNN architecture. Remember that one, which is Musk RCNN, and just quickly go through it as we have already seen faster RCNN. As Musk RCNN is just a simple improvement over faster RCNN. So let's get started. I think we could do something like this, and it looks a lot prettier, I guess. So yeah, you can see it well. Nice. So I'm not sure, but I guess some of you have taken, that computer vision course with either Professor Fahim or me. Maybe, I'm not sure if you did. But if you did, you would probably know that previously in machine learning field, we did not have the concept of deep learning and neural networks, which were, with convolutional neural nets, as you have seen, it looks, the first layers of convolutional neural nets are searching or extracting those lower level features, as we said, like the bridge of the nose, the angles of the eye shape, or stuff like that. So they're looking at a very, very zoomed in, detailed patterns that they're trying to recognize. And then further ahead we go in the convolutional layers, we're going to be seeing that it's looking for more complex patterns, like the whole face pattern, or the face of a cat, or maybe the body of a lion, or the body of a car. So yeah, so this is what the convolutional neural networks are doing. So they're both performing the feature extraction part, plus at the final few fully connected layers, they are performing the classification part. But this was not always the case for the field of machine learning. Previously, what we had was the concept of feature extraction as a separate, as a completely separate, of course, let's say model, right, or algorithm or heuristic. This is still being done in many, many applications, especially in things like industrial applications, where you have like a fully controlled environment, right? So if you are inside a factory, then you can control things like the lighting, you can control things, how the angles of the camera, where it should be, the angles of the objects that you're working with. So you can control literally everything. But if you are working in real life, this becomes a little bit more challenging, right? So for previously in machine learning, we had to actually do feature extraction manually. These feature extractions, some of them, especially for images, they were also based on convolutional operations, right? So what was happening before was somebody, like real engineers, their whole job was to find optimal weights for the, for the object in hand, right? So they would take the data that they have and they would tune basically the weights manually for those convolutional operations. And using that, they would be doing the feature extraction. So the feature extraction required a lot of human expertise, especially for images. It was a crazy amount. And then once these, these weights would extract some features from the images, later on we apply, of course, whatever classification algorithm they had, and that gives us the output, whether it's a car or not a car. And nowadays, in our deep learning field, the best thing about it is that it's able to do very good feature extraction plus the classification at the same time. Now, that said, do not underestimate the power of feature extraction, especially if you are in a field with not a lot of data. So if you are in such cases, feature extraction is extremely helpful for the model to learn a lot better, a lot faster with much fewer data. So things like if you are working with, with medical data, you could try to add things like angles between some bones or whatever. You could try to help the model learn better. If you are working in, what are they called? Financial data, then you could try to put in some algorithms or some laws for financial laws that could help basically the model learn better or find different patterns much faster. And this leads us to autoencoders, right? So the autoencoder's job is to encode the input in a much smaller code that is very useful for further tasks, right? So the goal of autoencoders is not just to do any classification itself or to perform any useful task within itself, The only job for an autoencoder is to extract extremely useful features that are as high level as possible, as condensed as possible, and will be very useful for performing future tasks, be it classification, generation, whatever it is. The goal is to make this code in the middle as good as possible. So this code in the middle, we're trying to make it, as we said, as good, as useful for future tasks as possible. And how do we do that? We, or the people who made this, they figured out that there is one big problem with most convolutional neural networks is they don't have enough data. But the problem is not the lack of data per se, it is the lack of annotated and labeled data. So we have a lot of data outside, right? We have millions of pictures on the internet. I think even trillions of pictures on the internet, and it is available, right? So you could use at least a big segment of that is easily available for you, and you could just train whatever neural network that you want on that. The problem is it would take hundreds of years for human beings to actually annotate that amount of data, right? The solution was to include a unsupervised technique that allows us to extract this code, very small, very condensed, very high level code that could be very useful to other supervised tasks. So in this unsupervised manner, we're going to learn a representation or extract a feature that is very useful for future supervised tasks. So that is the goal, or the initial goal, of autoencoders. It was to help as a good start for supervised learning models using unsupervised techniques. How does it perform this unsupervised thing? So if you have just the image, what can you predict, right? There's nothing to predict if you have just the image. And that's exactly the point, right? You have just the image, you will be predicting just the image itself, right? So basically what's going to happen is the encoder is going to take, let's say, a 40 by 40 image, right? So how much is 40 by 40? 800 pixels. It will convert them, let's say, into 20 values, just 20 pixels. And then from these 20 pixels, it will go back to 40 by 40. So you see this output in here? This is the output of the model, right? Completely useless. Why would I need a very bad representation of the image that I just put as input? So I don't need the output. What I need is the code, right? I need a good feature extractor. I need the ability to extract important features from the image. And that's what we get in this code in here. So the code, or what we call also as the latent space, encoded space, Z, you can see it referred to in many different ways, but the most important thing is that it is the output of the encoder in here. As we said, the encoder takes in an image and spits out a vector, one-dimensional vector. And the decoder takes a one-dimensional vector and gives you an image. So here we go, image, one-dimensional vector into an image. The whole reason why... Yes, absolutely, yeah.
So we had matrix 40 by 40. We put it in encoder and get one vector of the size 20?
Yes.
Okay, thank you.
Yeah. And then from this vector of size 20, it should have very condensed representation of the input. And we basically generate the same input, but as the output. So this is the output of the model. We're trying to make the output as similar as possible to the input. Of course, the loss function here is very simple. As you already can imagine, these pixels are just numeric values. So what you will be doing is you will take take this numeric value and this numeric value and use MSE. And then what you will do is you will take the average across the whole image, and that gives you the loss function of your model. So the model is just being trained on the simple reconstruction loss. Reconstruction loss is just basically MSE, but at every individual pixel value, right? So mean squared error, you have seen it for regression. The goal for regression is to predict only one value. The goal for this model is to predict each individual pixel value, right? And here we reach the basically understanding or the global understanding of autoencoders. So autoencoders, their job is to perform very similarly to a zipping file, right? So you take an image and you just zip it, you know, or RAR, right? Whatever those are. So you're compressing basically the information in your file in a very small representation that can later on be also decompressed into the same input, right? Of course, the output here is going to have some errors. As you can see, it's not perfect as the input, but we are willing to basically lose a little bit of the details that are not useful for future supervised tasks. So yeah, the encoder's job is to perform the following. It takes an image and it tries to extract some features. Here, we're trying to simplify the understanding. So just remember, this is not what's actually happening under the hood. So under the hood, it's not really creating a feature for smile, a feature for skin tone, a feature for these things. It is creating some features that are only machine understandable, right? So it's creating features which are not human understandable, more features that are machine understandable for future, what are they called, supervised neural networks to be trained upon. But just for the sake of for humans to understand, so it's trying to do something like this, takes an image, encodes it to some features that it can later on use to reconstruct the same input image. So here, whether the person is smiling or not, here clearly the person is smiling, so this feature is maximized. Skin tone, this person is a little bit on the darker side, so the skin tone is 0.85. The gender, clearly this is a male, so the gender is -1. The beard, clearly this person has a beard, so the beard is 0.85. Whether it has glasses or not, clearly it has no glasses, so it's 0.000 something. The hair color, it's a very dark hair color, so it's 0.68. And then,
Sorry,
of course,
can I ask again?
Yes.
On this picture, we see that we have input that is the same as the output. However, with these parameters, we can generate infinitely many pictures of humans.
Nice. Yes.
So is it guaranteed that after decoding,
No.
we will get the same picture?
No, and yes and no. Right. So absolutely, you're not going to get the same picture, but you are going to get something similar to it. So here, these features are not enough because you are replacing it with only 6 features. If you do it with 40, your accuracy is going to get a lot better. But it's never, ever going to be similar to this. So it's never going to be similar to the input, especially if your input is a high dimensional image, right? It's not, if it's an HD image, you're impossible for you to regenerate the same thing, right? It's going to be very, very different, but similar in the same way, right? So it's going to be very different from each other. It will have lots of, bad quality results. Autoencoders are not the best at generating pictures, right? So they are a very old model and a very old architecture to generate pictures, but they are very useful for understanding because they are the basics of, the new diffusion models that you're seeing out there. So yes, they are never going to be generate the same input and output. It's going to be very bad and very different results, but they will be very similar also at the same time, right? So yes and no. Now, just to agree on the terminology, the encoder, its job is to go from input to code, and the decoder, its job is to reconstruct the input from the code. So it takes code, gives you the input again, and the output of the model in general is going to be exactly the input, right? So the output is going to be as similar as possible to the input. Applications are absolutely endless, right? So here is an application that we did for domain adaptation, which is just a more mathematical version of transfer learning. So you have to go a lot more into detail with domain adaptation than just typical transfer learning. Or other applications are in things like anomaly detection, monitoring, model monitoring, data monitoring, and etc. So applications are absolutely endless. Another application is reconstructing corrupted data. So you will take a noisy input image like this and try to reconstruct a denoised version. Now the question would be, how can you get this pairs of noisy and denoisy image? As we said, the input for the encoder, autoencoder, must be exactly equal to the output. The difference between a what is it called, reconstructive autoencoder is, before we apply this input, we take the input, we add noise to it, and that gives us the new input. Let's say input noisy. Put it through the encoder, this gives you the code, put it through the decoder, this gives you the output. Now your autoencoder is not going to try to replicate this input noisy, it's going to try to replicate input in here. So just the only difference between this, what is it called, between the autoencoder and the reconstructive denoising autoencoder, is that we will have this step of adding the noise. And then, of course, we will be predicting the denoised image or the original image. And this leads to building a model that can clean up images. So things like, for example, you take those, I don't know, war images for your grandparents. For example, you might have some grandparents who have died, but you have like a very old picture of that grandparent or that grandmother, and that image is extremely noisy. So you could use something like the denoising autoencoder, and it would give you an image of your grandparents, but it looks very realistic with colors and no, it's not very broken, and the face is very clear and stuff like that. So denoising autoencoder, absolutely a wonderful application of autoencoders. The performances, as we said, are never going to be looking very good, but the idea itself is extremely useful, especially if you apply the same concept for things like GANs. The results are going to be a little bit better. But if you apply things, if you apply the same idea to things like, how to say this, what they called? Diffusion, yeah. If you apply it to diffusion models, exactly, you will get much, much better results, and the results are actually beyond perfection, right? Better than the real life. Here we will see just a couple of examples of autoencoders. So we have the undercomplete autoencoder, which we have been discussing. This is the most common architecture for autoencoders. And then there is the overcomplete autoencoder. The difference is very simple. The size of the code for autoencoder undercomplete is much, much smaller than the size of the input. Whereas for overcomplete, it's the opposite. The size of the input is like this. The size of the output is like this. The size of the code, this is the code, this is the latent space. This is the input. Now the question is, why would you do that? This seems like a very stupid idea. Why would anybody try to encode this into a much bigger version of itself and then reconstruct this small part? Because it's very simply just going to keep all these values, let's say put them here, and then copy them again here. So there's no learning. It's a very stupid idea. But the idea becomes very interesting when you apply other constraints to it. Some constraints might be like, yes, you might have a very big code in here, but let's say 90% of these values should be set to 0. So you're going to be learning a vector representation that is very big, but extremely sparse. Sparse means that the majority of them are turned off, or the majority of them are like zeros, absolute zeros. And now that thing makes it a lot more challenging, because in reality, you will be learning also a very small C. So the actual values that you will be learning are much smaller. It's just that the size will be bigger and the majority of the other places will be set to 0. The final one is what we have already seen. It's the denoising autoencoder. There are other types of encoders, but these are the most common ones that you will be seeing, especially if you're going to be doing a little bit of research or industrial applications, as we said, like monitoring your data or monitoring your model results. variational autoencoders. Now things become a little bit more difficult. So let's take a quick break from these types of autoencoders. Sorry, 5 minutes break, and then we come back with a much clearer brain. Take some drink, take some water, maybe a little bit of coffee, and come back, and we will be discussing about variational autoencoders, and we start the what is it called, the segmentation part of the lecture, right? So far we're just speaking about taking an input, reconstructing the same input. Soon we will be seeing the concepts of segmentation and how can we do it with autoencoding. So yeah, let's come back after 5 minutes. All right, so we are back with autoencoders. So far we have seen what autoencoders are. We have seen how they can perform the feature, what is called the feature extraction part of the whole classification or whatever supervised task you're trying to do. Usually, as we said, how do we do it? You just take a lot of unsupervised data, train your encoder plus the decoder. Once they are trained, you completely destroy the decoder, take the same encoder, add a classifier, which is just a multi-layer perceptron or fully connected neural network, and then freeze the encoder and train this setup with the supervised data that you have. So if you have a few amount or a very small amount of supervised data, then this idea is very good for you, especially if you're performing just basic classification. So it's a very simple, very basic idea to do if you have, as we said, a lot of data, but that is not fully labeled. So if you have a lot of unsupervised data. Now, variational autoencoders are very similar, but yet extremely different. So now let's imagine that we're no longer speaking in terms of an image, but just a vector. So this is a vector. These are the input values. And this is also another vector. This is the output, which is the kind of duplication or let's say the reconstruction of the input. Previously in the encoder, we used to get one-dimensional vector, let's say of size 20. For the variational autoencoder, we will get two one-dimensional vectors, right? And each of them will have a size of 20. So we will have what is it called? We will have 40 values in total here in this setup. We will have 40 values. And these 40 values will be split into two vectors. One vector is for the mean, and the second vector is for the variance. Can somebody tell me what can you do with mean and variance? What does that give you? When you hear these two words, what is the first thing you think of when you hear these two words? Let's see. Sample from what? From a? This.
Maybe normal distribution.
Absolutely. You will be sampling from a normal distribution of mean M and variance V. So the difference is, instead of, as your friend, remember what your friend said, we will be taking an image, extracting a very hard-coded features, and then reconstruct from these features the input image. Your friend has said that these features are very similar to other images, and they could be used to generate different pictures. So if I say that smile is 0.99, or I say smile is 0.98, is there a big difference? Absolutely not. So with variational autoencoders, you're able to represent exactly that. But instead of saying smile is equal to a single number, you will give a mean. So let's say this is it. Here's the mean of smile. And the variance, let's say it's 0.001 or something like that. And this gives you a range of smile values that you could sample from, and they will all be extremely similar to your input image, right? So instead of having, like, let's say a single value here of 0.98, now you have a range of values that you could choose from, and all of them would lead to a similar output image. This leads to the model learning a lot from the same data. So it's the same image, but let's say you will sample like 100 times from this image. And each time of these 100 times, you will get a different value that could be used for the decoding or the reconstruction. And this means it's kind of a, let's say, augmentation per se, right? So it allows the model to learn a lot more from a smaller data set, allows it to learn a lot more in depth from those same exact images. And this basically leads to this latent space being extremely smooth, right? So if here, for example, let's say this is a smile, the next image was here, the next image was here, the next image was here, let's say the next image was here, the next image is here, the next image is here. Even though if you have a lot of data, they're all going to be, you know, these discrete places, locations where you have never seen an image with this value. I've never seen an image with this value, never seen an image with this value, same thing here. So your latent space is not very smooth. Whereas when you are discussing with, what is it called? Variational autoencoder, you will be taking all of these values, let's say for here, some of these for here with some intersections, some of them from here. So you will kind of be seeing a lot more of your latent space, and you will be using all of these to reconstruct images, making your latent space more smooth for the reconstruction, and your reconstruction quality much better, and even your feature extraction abilities more accurate and more generalizable. So here was what we were discussing. You will take, for example, this boy is very sad, he's not happy, he's not smiling. Clearly, it's in the negative, but is it important that it must be 0.659, let's say, or any of these negative values could actually do the job and reconstruct the input image correctly? So yeah, it's not important to have a specific value. Having this kind of distribution performs much better, allows for much smoother reconstructions. Take something like the Mona Lisa. We don't know if she's smiling, if she's not smiling. So it's definitely in the zero. But as you can see, since it's very confusing, the model will give it a much higher variance for reconstruction. So this, very big. We're not sure where it is at all, right? So it could be smiling, could be not smiling at all, but it's much closer to the zero. This little girl, clearly she is smiling. So you see the variance here and the variance here are completely different. This one is much, much bigger than this one. And this one is even clearer that he is very much smiling. And the variance is very small. So this is what the variational autoencoder does. It just allows you to get a more samples from the initial image than what you actually have in the data. So here you will take your image. Remember, previously we had just a single value. Now we have a distribution of values that we could sample from. As you know, sampling is a very simple technique. In Python, there is a library. You just give it the mean and the variance, and it gives you the actual sample, and you could reuse it 100 times, and it will give you 100 different samples from that same distribution. So here you will have, as we said, instead of a single value, you will have a distribution. And how do you represent the distribution? With two values. How do you represent the distribution? With the mean and the variance. So it's basically just doing the autoencoder, but twice. That's it. And then you get the decoder. So from that latent space, which is now a distribution, you would just be sampling multiple times. So for example, here, smile is 32. Here, smile is 17. Very small difference. And that gives you different samples to choose from, and that gives you different, what are they called? Similar or different and similar decodings or different and similar reconstructions. That leads to more training images being passed through the decoder and more samples being used to actually do the classification later on. That means the model is going to be much, much better and more accurate for performing your classification later on. So that's it for variational autoencoders. They're a very simple concept, as we said. The only thing that they add is that idea of what is it called? Of a mean and variance, which is just doing the job twice. The loss function, on the other hand, is completely different from what we discussed. So previously, we were just saying mean squared error. That's it. But now the goal is those two values are, which are mean and variance. How can you force them to act accordingly to become a mean and the variance? That's the final step. And for this step, I'm not going to explain it to you guys. You could either look at it through just the YouTube videos, pretty simple, or you could do it with hopefully in the advanced computer vision or the advanced machine learning modules. And the other idea is how to make the sampling. Remember when we said sampling? How can you make that a back propagated or a differentiable operation? Because sampling is just a code, it's a function on Python. You cannot, find the derivative of a function in Python. What is the derivative of an if statement? What's the derivative of a for statement, right? So you cannot do that, although it is a very big integral part of our variational autoencoder. So yes, this is also another very simple trick that could allow you to basically make the sampling part outside of the neural network and yet keep the variance and the mean as a singular part of the neural network. So the mean and the variance will be differentiable, but the actual sampling will be taken outside of the neural network. Very simple trick, but hopefully you will be seeing it in the future courses. And now for the actual reason why we are studying autoencoders, which is the segmentation. So there are two types of segmentations. There is semantic segmentation and there is instance segmentation. For semantic segmentation, it's very simple. You choose the pixels which belong to a certain class. All of these pixels belong to the class human, and they are all together like this. These pixels belong to the class table, so they all belong together. Whereas for instance segmentation, we don't just care about the class, but we care about each individual instance of that class. So this is a human. This is human number one. This is a different, completely different human of the same class, which is human, right? This is an instance of class human. This is another instance of class human. This is a third instance of class human. So we are differentiating them. Here in semantic segmentation, we don't care. We just want what is the pixel that belongs to the class human. Human 1 or human 2, I do not care. I just care about the class. Here, I do care about the actual instance of that class. 6. And this is another object which belongs to the class table, number 1. So this is the main difference between semantic segmentation and instance segmentation. They're both segmentations. They're both going to give a different class or to give a different value to each individual pixel. So that's what they worry about. They worry about the pixel value or the pixel level classes. But for the semantic segmentation, it just worries about all the instances of that class, regardless of the differences between them. It doesn't specify this is instance 1, this is instance 2, or this is a different instance from this one. They're all the same. For instance segmentation, it focuses on the instances specifically. And of course, it does give you what is the class of that instance. So it tells you that this is object number 1, and it is a human, and this are the pixels. This is object number 2, and it is a human, and these are its pixels. Same thing for the table, same thing for the other objects. So we're not going to go into instance segmentation for now because it's a very simple thing to understand once you learn about semantic segmentation. So we will first start with semantic segmentation, and the first architecture for semantic segmentation, of course, is autoencoder segmentation. So the basic model that we have been working with so far. Remember, you take this image, put it in, I don't know, supervisedly or in RoboFlow, and you will be doing the segmentation manually like this, segmenting all of the borders for these two people, and they are all of the same class, right? Your output will be this. This is called a pixel map, or this is called a output segmentation. This is your segmentation, right? This is what you're trying to predict. And remember, with autoencoders, what they do, they take in an input image and they try to generate a output image. So they take in an image and gives you out an image. So instead of predicting the same input and same output, now we're just simplifying it or changing it. This is the input image, and this is the pixel map. The pixel map is basically where is each individual class located in that image. So it has 244 by 224, which are the same sizes. Here it is 3 channels because it's RGB image. And here it is N channels. So N channels refers to the number of classes. Each channel is let's say, specifically training to find objects of that same class. So channel number 1 is looking for cats. Channel number 2 is looking for dogs. Channel number 3 is looking for humans. And in the same way, with just basic mean squared error and a lot of data, you will be able to train a very good segmentation model for using a simple autoencoder and whatever data set you have just trained. So this is the trick to basically train whatever segmentation model you would like to do, or an autoencoder segmentation model on whatever data set you are trying to train on. It's definitely not the perfect model for this occasion, mainly because, as we said, autoencoders, they don't work very well with large scale objects, or images which are HD. Do you have any questions so far? Nope. Okay, seems good. So let's continue. Now we go from the convolutional neural network model, or the autoencoder, which could be any model, into the convolutional neural networks. So this model is called fully convolutional neural networks. And as you can see, its abbreviation is FCNN, which is the same thing as fully connected neural networks, right? But this is the absolute opposite of a fully connected neural network. So this is the fully convolutional neural network, and this is fully connected neural networks. In the exam, every time you will see the word fully FCNN, I must give you the exact definition. Is it a fully connected neural network, or is it a fully convolutional neural network? They are complete opposites of each other. Fully connected means it's only using multi-layer perceptrons, or it's only using connected layers, which are just basically linear layers, right? The neurons that you have seen before. And fully convolution, it just means it does not absolutely use the connected layers. So there is no connected layers in here, or the fully connected layers in here. There are no multi-layer perceptrons in this model. None, absolutely none whatsoever. So what it does here is simply takes your input image, and this is the encoder. Remember when I said the output of the encoder is a one-dimensional vector? Before it gets to this part, it stops. So what it does is the following. Takes in an image. This is the image. Let me clean it up. Here's the image. Puts it through a convolutional layer. You get an image. Puts it to another. You get another image. You get an 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 image. And every time you put it through a convolutional layer, the size of the image gets smaller. So this is the size of the output image. That's it. The model stops here. There's no more a conversion to a one-dimensional version, one-dimensional vector, and there is no more what is it called? A decoder. So it is exactly just here. So it stops basically before we get into that part and performs the segmentation on this image. Remember when we were speaking about things like, what is it called? About interpretation, right? Or interpretability. And we saw that the actual convolutional feature maps, they do contain a very good information or amount of information inside them relative to what is happening in that image, right? So those convolutional feature maps are very useful. And this is where this model, what this model relies on. It just basically uses the convolutional feature maps and tries to convert them using another convolutional layer to a class feature map or a class pixel map, like this one. There are multiple versions of it, basically depending on the stride. So the worst version, which is the version that makes the size very, very small, this is something that is very easy to train. And as you can see, this is the ground truth. And there it is. So fully convolutional neural network 32 stride means that the output, this image, is 32 times smaller than the input image. So it's much smaller, and meaning every group of 32 pixels will be grouped together into the same, class. And that leads to very bad, of course, separation of the classes. So you can see this in here, this angle, you cannot even see it in here because they're all just merged and smooshed into the same pixel. So this fully connected 32 is pretty useful because it's super fast. It provides very good results on low amounts of data, but it does not give very good results if you are working with a very accurate situation where you need very accurate and detailed oriented segmentation. The other version, which is fully connected, fully convolutional neural network 16 stride, means that this output image or the segmentation is 16 times smaller than the input image, which means it's very bad, of course, also, but it's a lot better than the 32. And it's also much slower than the 32, requires more data to tune. So this is, you can call this the simple and fast. This one is medium or medium results, medium speed. And this one is best results and slow speed, right? Very slow. This one is the 8 stride, and it means that this image, the segmentation is much smaller than the actual image by 8 times. Of course, fully connected convolutional neural networks are not the best thing for segmentation. And this leads us to the next part, which is SegNet, which is just a very small intro to UNet, which is the architecture we'll be spending the most of the time with. But for SegNet, it's basically a simple concept. You take an image, this is the input image, and you build an encoder decoder setup, just like we've seen before. All of them are convolutional layers because autoencoders, you could have, fully connected layers, you could have some multi-layer perceptrons, you could have whatever you want. But here, all of these layers are by default completely fully convolutional layers. You can have some pooling, like max pooling and stuff like that, but you absolutely cannot have any any fully connected layers. So here you will have the encoder part, here it is, plus the decoder part. The only thing that gets added in here is that the decoder is the mirror of the encoder. So previously, we did not put any restrictions on how many layers do you have on the encoder, how many layers do you have on the decoder, what is the shape of the encoder layers, the output of the encoder layers, what is the output of the decoder layers, and all of that, we did not put any restrictions on it. For this one, it does. This one, it just puts restriction that each individual layer in the encoder has a replica or an opposite version, a mirror version on the decoder. As you can see, the type of layers that we have are very simple. Convolutional layers on the blue, pooling layers with the green, we have already seen that. These blue ones in here are also convolutional layers, so it's the same, just a convolutional layer again, convolutional layers, convolutional layers. This is softmax, which is basically, what is it called? Which is basically, just a activation function that just makes it between 0 and 1. It's very important. It's similar to sigmoid, but instead of working with only one class, it works for multiple classes, and it makes the numbers, all of them between 0 and 1, and all of them, they sum up to 1, meaning all of this is the distribution values, meaning they are all pretty easily interpretable by human beings. But just as you see, softmax here is just another activation function, as we said, similar to sigmoid. ReLU, you know it, very easy. Batch normalization, also you know it, very easy. Upsampling, maybe you don't know it, but we did speak about it for the YOLO. What it does is it takes, let's say, pixel like this. This is the input image. 1, 5, 5, 10, let's say. And it gives you the following image. Let me do it manually. So here 1, here is 10, sorry. Here is 5, sorry. And here is 5. So what it's going to do is going to put values in here. So let's say this is through 2.25. And another value in here is 3.75, let's say. Same thing here, it's going to put, let's say, just 2 and 4 to simplify. This here between 5 and 10, it's going to put 7 and 8, let's say. 7 and 8. And then in the middle, it's just going to also do the same thing. But between 2 and 7, you have, I don't know, 5 and, let's say, 4 and 6 instead of 5 and 6. 4 and 6. Here between 4 and 8, you will have, let's say, 6 and 7. And 7. So this is what basically the upsampling does. It just takes your input image, whatever it is, and it makes it double the size. And how does it do that? It just finds the 2 pixels that you have already put, so 1 and 5, and tries to build a line, a linear line between them. So this one, let's say, is 2, and this one is 3, this one is 4, and this one is 5. It just puts whatever values that it can between those 2 values to make it a little bit bigger. That's all it does. So it's just a simple calculation. It does absolutely no work in terms of learning or training or back propagation. It's completely useless. So this is what Segnet has proposed. UNet, as we said, it's the improvement over that, and it adds in a very simple thing, which is this U shape, very similar to what we have seen before. Remember the mirror here. Each set of encoder layers has their corresponding set in the decoder here, 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 here. So each part of the encoder has a mirror on the other side for the decoder. What gets added is this copy function. So all of these you have already seen before. You know them. The copy part, is what is interesting. So the copy part is what UNet has added. And it's also very much alive and very much used in the, what is it called? In things like YOLOs and the different versions of the YOLOs. But simply what it does is it will take the output of this layer, the convolutional feature map of this encoder layer, copies it as it is to this mirror in the other side. So the convolutional feature map will go here, and of course will go here too, right? So it will go as input in here, and in this place it will be concatenated with the input. So this is the convolutional feature map in here, comes here, comes to the opposite, and then you go down to the next level of the encoder. Here you go, there it is, and then you copy it to the other side, and of course you bring it to the next level of the encoder. Next level of the encoder does some work, takes the convolutional feature map, puts it in front of it in the other side, and then brings it down to the last layer of the encoder. Last layer of the encoder encodes it, finishes up, and then this is the first layer of the decoder. First layer of the decoder will take this convolutional feature map with this one, concatenates them together, so it will be a very big convolutional feature map, and then puts it through the decoder. Again, you will have a convolutional feature map coming from this side and another convolutional feature map coming from this side. They have the same sizes because of the upsampling, and then you will merge them together into one big image, puts it through the decoder. Decoder gets in, you have another input, convolutional feature map from here, convolutional feature map in here, merge them together, put it through the decoder, and there you go. You have your final result. You have your final segmentation. And how will it be combined? Just concatenated. How do you say it? Like this. Let's say that this one contains 1, 2, 3, 4, and one channel. Let's say it has just one channel. There is another image that comes from the other side, which is like this. 4, 5, 6, 7. What you will do is you will put them together into the same image, but different channels. So you will have channel number 1 is this, channel number 2 is this. So you will have a much bigger channel. So let's say from this side, you have 12 channels. From this side, you have 12 channels. So the input to the next layer of the decoder will have 24 channels. So they're just merged together as different channels. That's it. Now the question is, thank you. Now the question is why? Why would you do that, right? So the goal of the encoder, why do we use all of these encoders, is that we try to learn very high level information, right? So all of this pass like this from the encoder through the latent space to the decoder, we're trying to get a very big understanding of what's happening in the image, right? So as we say, the more convolutional layers you pass through, the more abstract the features you are extracting. You're extracting more abstract features. The problem is when you are extracting too abstract features is you will forget the details. But for segmentation, you need the details. So that's what UNet does. You have this path which focuses on abstract features, and these copy paths which focus on giving as many lower level details as possible to the decoder layers. This allows the decoder to have both abstract information, abstract info about global picture, and details about location of objects. So this allows it to be very precise, and this gives the best results so far for instance segmentation. Of course, there are new variations of it every second coming out, especially if you're working for a specific field, a medical field or another field. There are specific pre-trained models for UNet that already pre-trained on large models like this. And for for other algorithms, they use different types of loss functions, different trainings. It's up to them, of course, to make these improvements. But for you, the UNet architecture as it is like this, it's already more than useful for getting started, of course, both in research and in results. So this is it mainly for semantic segmentation. Do you have any question about semantic segmentation for now? Semantic segmentation. So it's a very simple one, very basic, nothing too fancy, nothing too complicated, I hope. But still, it is very, very much useful for your future and of course for your research work. So this is it for the UNet. If we're good, let's go to mask RCNN. So this is going to be the final part of basically our mask RCNN or of our RCNN family, and also the final part of our segmentation lecture. Remember, with faster RCNN, what do? Take an input image, passes it through the region proposal network, RPN, gives us the regions of interest or potential object locations. From that, you take these and then perform ROI pooling. Here it is referred to as ROI alignment, region of interest alignment. And then from there, you will just send it through classification and bounding box. So here. So this part, you already know it. This part is the faster RCNN. So faster RCNN, kind of what it does is it takes a big image with multiple objects and gives you small images with only one object. So if you have a small image with only one object and you would like to do segmentation, you would like to do instance segmentation, what can you do? Just perform basic semantic segmentation on it. And since there is only one object and one class in that specific small image or region of interest, then your semantic segmentation, so let's say this is it, this is the semantic segmentation, performs the semantic segmentation for that specific instance. So in reality, instance segmentation is equal to object detection plus semantic segmentation. So this gives you basically the understanding of how can you perform instance segmentation. It's very simple. Perform object detection on each individual instance, get that image for only that specific instance, and then segment that small image using any segmentation or semantic segmentation idea that you have seen so far. And that's going to perform for you your instance segmentation. Pretty easy, pretty simple, very straightforward, very logical. Any ideas about the lecture, about segmentation lecture? All good? All right, so let's take a quick break and let's come back for a very quick lab about segmentation. This lab is going to be almost like half an hour. So we're going to finish it in super quickly and you'll be free to go for today. So this will be basically the final part of the computer vision part of this course. The future lectures will be about MLOps and natural language processing. So we will see about the order, of course, in the future. But for the majority of the future lectures of this course, it's going to be mainly about your projects, about the midterms, midterm evaluation, of course, and the mid-project evaluation, and about the homeworks. And of course, the rest will be not so much included in the final exam. So even about the questions of the final exam, they will be more specifically oriented towards computer vision part, mainly because I was informed that you will be having other courses where you will go in much more detail about natural language processing. So for natural language processing, we're just going to be doing the basic to get you started on at least building models for natural language processing for your company. But other than that, if you want to go to the details and you want to learn the theory about natural language processing, definitely you will be getting more courses coming soon in your. When will the final be? Yes, I actually got the dates like right now. It is Tuesday, 25/7. Here. So what's going to happen is the next week, we're not going to have, the next weekend, this weekend that is in front of us, we're not going to have a lecture, mainly because it will be sadly on the same time that I'm going back to Paris. The Monday lecture, we will be, of course, having it. During the Monday lecture, we will have your project presentations. So that's going to be focused only for your project presentations. The weekend right after it, we will have the midterm exam. So the Saturday, the 15th, we will have the midterm exam. The Monday afterwards, we will have hopefully a couple of lectures and labs. And then the Saturday that is right after it, we're going to have a long, project presentations. So we will try to find a period for it so that everybody can attend, but it's going to be at least 15 minutes per person or 15 minutes per project. And of course, just the 1 hour and a half that we have is not going to be enough, but hopefully it's going to cover at least everybody and everybody's going to present. So please do prepare all of your projects much earlier, as fast as possible, because by the Saturday 22nd, we will have the project presentations and you will have your final grade for those. All good? I will send you the dates, of course, on Zoom, not Zoom, on Telegram, and I will try to put them as deadlines on what is it called, on Moodle, so that at least you can have them ready. So great, let's take just a 5 minutes break as usual, and let's come back for the lab. The lab, as I said, is going to be extremely simple, extremely basic, very quick. We have already done the lab. It's just going to be looking through it again with the faster RCNN, and hopefully it will be pretty easy to understand. Okay, see you soon, guys. Hello, hello, and let's finish the lab part. Tac, tac, tac. There it is. So for the lab part, we're just going to do basic detection 2 using what is it called? Mask CNN. So what you do is you come to the detection 2 on Google, find your, what is it called? Colab notebook, and you get started. So now let's try to hopefully go through a little bit more details about this part. And it should be extremely fast, so that's good. Hopla. So we've already spoken about the get config and how you can use it and the default predictor and how you can use it. So honestly, I think this lab is going to be extremely fast. But before we go there, we just want to take a look at the output and how does it look like. So it's going to be doing a little bit of work. Has anybody tried to use, what is it called? Faster RCNN or mask RCNN so far on their images? Nope. All right, let's see. So this is the output of your predictor. And it's a very simple dictionary. Most of the concepts in here are going to be in CUDA. So just make sure if you are going to include it in whatever dashboard or something like that, just make sure that you handle this correctly because it's going to be a very major issue later on. And you're always going to have some bugs like about this, especially if you will include some interpretability or model monitoring. This is always going to be a bug that you'll have to continuously fix. But other than that, so you'll basically get instances like this, and then you will get the summary in here. So the number of instances, the image height, image weight, and then just a couple of fields. In these fields, you will have the following: predicted boxes. So these are the actual bounding boxes. And then you will have the scores. This is the confidence score for each one of those. And then you should have, this is the predicted mask, as you can see, false, 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 false. And some of them in here in the middle are going to be positive, meaning true. Maybe, do you see any true in here? No, you don't. So basically, yeah, we don't have anything on the borders. That's why you don't see any true. But there is going to be a lot of truths inside. So this is how you basically give the results for your, what is it called, for your prediction. And in this case, for example, let's look at it. Sorry, let's look at it in here. That true false map is going to just give you these exact segments in here. So it's referring to each individual pixel. Does it belong to the class or not? Each individual pixel level, right? And the information about the class, what it is, you will find it here in this field called predicted classes. So each one of these, you will have its score. So this is the score. And here you will find the bounding box of that specific object. And here you will find the basically the, let's call it pixel map or whatever you want to call it, for that specific object too. So as you can see, it's very much detailed and provides you with everything you might want to get a very beautiful, you know, what is it called? Software around it. But if you want to do just with the basics, they're also being done in here. So you have the visualizer, which allows you to basically visualize the results in here. And as you can see, for example, something as simple as just mapping from the class index in here, so number 17, to the actual name of that class is also being done immediately. So it's amazing results, very good overall. As you can see, the confidence thresholds or confidence scores are much higher than what we have seen, for example, for something like the nano YOLO V8, but they are very similar to something like the X YOLO V8, so the larger version of YOLO V8. And that's mainly because of size, as we said. Bigger models tend to be more confident about their results, even though they could be more wrong about their results. So if the results are wrong, they would still be very, very confident about what they said. And then, of course, in here, as we discussed, so you will be taking these individual regions, create this, take basically these all points X, all point Y, convert them into this polygon, and this adding 0.5 is just there to make sure that you don't have anything on the border. So just make sure that everything's clean, but just to escape running into what is it called, bugs, right? And here everything is perfect. You take the polygon. This is the bounding box. As we said, this is one way of representing the bounding box. This is the polygon. You just send it directly, and the category ID would depend on the ID that you send here. So if you send balloon is number 1, so balloon is 0, and person is number 2, so balloon here, person, its category ID is going to be number 1. So it depends basically on the array and the order inside this array that you would be sending when you register your dataset in the dataset catalog and update the metadata of your dataset in the dataset catalog. Here you will be just visualizing it, making sure that you're reading it correctly. And then for the training, immediately gets done. As we discussed, you just specify what is the architecture that you would like to use and what are the weights that you would like to start from, right? So this is kind of like the fine tuning that we discussed earlier. As you will see in here, you don't need to do anything. For YOLO V8, YOLO V5, and faster RCNN, you really don't need to do anything to actually get started doing the fine tuning. But if you're using YOLO V4, as we said, you will be fine tuning it manually, setting this to the correct number of classes for each individual layer, setting the number of filters to the correct number of filters at each individual layer. So you will be doing a lot of the heavyweight of the fine tuning manually. Whereas for YOLO V8 or YOLO V5 and this, what is it called, faster RCNN or mask RCNN, all of that fine tuning steps are being done automatically for you. You just need to set this number of classes in the configs, and automatically it's going to set up which layers must be changed to what specific sizes, and decide which ones get used from the pre-trained model and which ones get created from scratch. And then, of course, you try the training. Training results are pretty simple. You look at the results, you validate them. You could apply them into on what is it called? So you could apply these results. Here you will see things like the MAPES. Here is the, let's take a look. So this is the mean average precision that we usually discuss. This is the average precision at 50. So this is the actual, what is it called? Sorry, this is the actual intersection over union that is used to calculate the recalls and precisions. This is again the same thing. And these are the different sizes of the object. So this is average precision for small objects, average precision for medium objects, average precision for large objects. These three are usually extremely useful if you're working with a specific type of data set and the data is either very small or very large or stuff. As you can see, for the large objects, it's never going to miss them. But for the medium objects, it's a bit harder. And especially for the small objects, usually your results are going to be horrible. These are the results, if I'm not mistaken, for the bounding box. Yes, this is the results for the object detection. And these are the results for the segmentation. And as you can see, for segmentation, the results are even better, a little bit better than the object detection, mainly because you have the big image like this, and you get to fine tune basically your results correctly. And usually because the actual annotation itself is very good, right, for segmentation. And here is basically what you will be doing. This is how you should be interpreting it. The area all, area small, area large, this is also pretty simple. These are the different intersection over unions. Remember when we said you will be taking different intersection over unions to calculate different precisions and recalls. Sometimes you will be taking that. Sometimes you will just take a very specific hard-coded value. Sometimes you will take 0.50, sometimes 75. Sometimes you will take the average precision And well, you will take basically the precisions and average them using the consecutive recalls. And sometimes you'll do the opposite and take the recalls and average them using the consecutive difference of precisions, right? So this is the mean average recall, and this is the mean average precision. Different ways of calculating the same thing, but usually the most important one is the mean average precision for all using this. So this is the number that you should be reporting in most cases for your data set. Average precision, intersection over union going from 0.5 to 0.95, area for all objects, max depths, I forgot what this is, but it's usually not that important if I'm not mistaken. And this is the actual value that you should be reporting. Other types of built-in models, you have like hundreds of other types of built-in models, such as, for example, key point detection. And this tells you, for example, where the head is, the shoulders, where is the hands, the legs, all of that, you see. And this is the panoptic segmentation. It's another one that is more oriented towards segmenting every single pixel on the image. So you're no longer just interested in only the objects that you're interested in. So for example, person and horse and something else, but everything in the image must be segmented. You could be running your inference on basically on a video, and you could do that very easily with this script that they already provided you with, and this is just to download it. So as you can see, actually going from a data set to modeling that data set, or to annotating the data set and then building a model and then training it and then uploading the results and using it for inference is very, very fast and very simple. Hopefully during the next lectures, we will be seeing how to use these models, how to deploy them in real life, and how can we build a very simple website that actually uses these models. Do you guys have any questions so far about what we have seen today? About what we've seen in the course in general, maybe about your projects. Remember, the project is like the majority of your grade, right? For, as we said, for the midterm and for the final exams, the questions are going to be very direct and very simple, but for the project, it's going to be very thoroughly evaluated. Any questions so far? All good. So hopefully we will be seeing each other during the next Monday. So please be prepared to present your projects this Monday, and be prepared to discuss it, show us your results. And if you have some final adjustments, I will be giving you an extra week. So hopefully the next week, the next Monday, we will be discussing basically your projects. If everything is good, we will be, or if there are some things that need to be modified, something that I might think you need to do more, so more validation, more testing, or a different idea. So you will have an extra week and a half, or maybe 2 weeks, to actually implement them and then present your projects again, and hopefully the results will be much better. So thanks a lot, guys, and have a great week.
Thank you. Goodbye.
Bye.
Bye-bye.